Started. Okay, the quiz, which is now too late to submit. All right. Number one, unfortunately, threw off more people than it should have. Maybe it was the wording, but the velocity of the projectile as it lifts off the ground. Okay, so you're supposed to plug in t equals 0 for that one. Okay, so anyway, y equals negative 4.9 t squared plus 19.6 t. Okay, so number one isn't asking only for the derivative, which you're supposed to do. So y prime was v, negative 9.8 t plus 19.6. Second derivative is negative 9.8, which automatically gives you the answer to 6. Negative 9.8 meters per second squared. Some of you know that's the acceleration due to gravity on Earth. Negative means it's pointing down. Okay, so the acceleration due to gravity is negative 9.8 meters per second squared. And some of you realize that from your physics class, perhaps. Okay, you're supposed to plug in 0. So v of 0 is 19.6 meters per second. Okay, so as the projectile lifts off, okay, that means you're supposed to plug in t equals 0. Okay, number two, maximum height. That means the velocity is 0. So you set the velocity equal to 0. That happens at 2 seconds. Okay, you were supposed to label units for all of these. Okay, 3, what is the maximum height? I plug in y of 2. So put a 2, whoops, put a 2 back here because we know that's the maximum height time. And that comes out to be 19.6 meters. This problem has a lot of 19.6s all over, as you have realized. Number 4, projectile hits the ground. That means you plug in 0 for the y, okay, and it comes out to be 0 and 4 seconds. You throw out the 0, okay, because it says hits the ground. 0 is the beginning of the experiment. So when is the height 0? At the beginning of the experiment, which makes sense. And then after 4 seconds, it comes back down. But if it asks when does it hit the ground, you have to exclude the 0. That's not hitting the ground, it's starting the experiment. Okay, so after 4 seconds. And 5, what is the velocity of the projectile as it hits the ground? Plug in 4, negative 19.6 meters per second. And acceleration, we already got negative 9.8 meters per second squared. Okay, so that's the quiz. Some reminders about the quiz. I grade quizzes a lot more leniently than I would exams. Okay, a lot of you didn't get number 1. I kind of let it go. Maybe the wording got you, but I may not be as kind on exams. Another thing, some people left off the units. So you have to have proper units. So meters per second squared, or even just seconds, and so on, right? And some of you used some principles that you had from physics. You weren't supposed to use that. So for instance, some of you said, well, it takes 2 seconds to reach the top. So obviously 4 seconds total. And yes, that is a principle for physics, that if there is no air resistance, the amount of time it takes for something to come up, let's say if it goes up in 2 seconds, it takes 2 seconds also to come down. And some of you argued that from physics. That's true, but you weren't supposed to use that. And by the way, that's not true if there is air resistance. But anyway, you're supposed to do it mathematically without your principles of physics. Okay, and one other side note that I'll mention that really didn't have anything to do with the problem too much, but notice the answers to 1 and 5. They had the same absolute value. Okay, it starts off at 19.6 meters per second. It goes up, it comes back down at negative 19.6 meters per second. The only difference was the sign. Okay, and that is a principle in physics, that if there were no air resistance, okay, the speed at which an object goes up. So if I launch an object, it goes up and then, it comes back down. It comes down if there's no resistance, air resistance, at the exact same speed, as you can see here. Okay. Another side note is that's the reason why on holiday celebrations, let's say they don't want you to shoot off, guns in the air. Okay, and you might say, well, I'm not aiming at anybody, I'm just shooting it up in the air. Okay, yeah, it goes up, and it comes up, but it has to come down, and when it comes down, it's coming down pretty fast. Okay, and actually, because of air resistance, it's not quite the exact same speed, but it's still going pretty fast. All right, so you just shoot a gun, right? The bullet goes up in the air, and say, I'm not shooting at anybody, so it's just going up. It's harmless. It comes down, so if it comes down randomly, it's coming down pretty fast. Because of air resistance, it's not quite the same speed, but it's still going down pretty fast, and you could hurt somebody with that, right? Now, if there were no air resistance, let's say if you do the experiment on the moon or on Mars where there is no air, then yes, indeed, whatever speed it goes up and whatever speed it comes down would be exactly the same. But on Earth, we have air resistance, so when the bullet comes down, it's not quite the same speed. It's still pretty fast. So that's why they say, you know, don't just randomly shoot bullets up in the air, because when it comes down, it's going to be pretty fast. And if there were no air resistance, as you can see, they are the exact same speed, except one's going up and the other's going down, right? Positive 19.6, negative 19.6 meters per second. Okay, so that was a little bit of physics with this question, but I wanted to get that out of the way. Okay, so we are done with that. Okay, game plan for today, the rest of today, is I'm going to try to finish up section 10. So we are here. Okay, so you know we're past the halfway mark when I get to this side of the paper, right? So once I get to this side, we're more than halfway. Okay, so I'll try to finish 310. So I have Tuesday and Wednesday to finish up 311, and questions and answers on Thursday, and exam Friday. It's been a while since we've had an exam, but we've had a couple of exams. You know the ground rules. You turn in all of this, right? And so again, on Friday, how do we do exams? So via Canvas announcements, maybe a little bit after 12, 12:01, 12:02, I will send you the exam, but I'll also project it if that's better for some of you. And then you definitely have to have your camera on during your test, as we talked about before, but mute yourselves. And if you have any questions, just put it on the chat. And then I'll close the class as usual at 1 o'clock. Then I'll give you 5 minutes to take pictures, you know, click, 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 you know, take all your pictures that you need on your cell phone, or if you have a scanner, scan it. So I'll give you 5 minutes to do that, and then you have until 1:30 to submit your homework. Although if you want to submit your homework earlier that day, you know, that'll be perfectly fine also. Okay, and you can have your one cheat sheet, so front and back, put any formula that you wish on your cheat sheet, and you can use a cheat sheet for the exam. Okay. All right, so let me get back to where we were on 3.10, please. So key ideas is the so-called linearization, page 252. You can use what they have in the text. I'd rather not. I'd rather just say it's the equation of the tangent line, which you already know, but write it as a function. Make it look like y equals mx plus b. So whereas before, I said, make it look like y minus y1 equals m times x minus x1. Stop. Now we're not going to stop. Just keep going. Make it look like y equals mx plus b. Call it L of x. So L of x is the same as y. And then we will use that to approximate the function sometimes. Why? We like straight lines. Okay. And the other thing is differentials. dy equals f prime of x dx. A little change in y is related to the little change in x by multiplying by the derivative. Okay, and again, one way to, if you had to memorize it, think of it as dy dx equals f prime of x, right? Leibniz notation, and then multiply both sides by dx, and it looks like that. Okay, so little change in y equals f prime of x, little change in x. Okay, so that's what we did last time. I'll do a bunch more, and that'll be it. Okay, so problem 17, y equals square root of 3 plus x squared, x equals 1, dx is negative 0.1, little change in x is negative. Okay, let's look at the problem again. Find the differential dy and evaluate dy for the given values of x and dx. So x is 1, dx is negative 0.1. So this is saying if x decreases by 0.1, how does y change approximately? Okay. So dy equals, again, think of this as 3 plus x squared to the 1/2 power, right? So 1/2, 3 plus x squared to the negative 1/2, then by the chain root times 2x dx. And 2 cancels in half. So this is x over the negative 1/2 over radical 3 plus x squared dx. I'll just plug in. So they told me x is 1, put a 1 right there and there. Dx is negative 0.1, so negative 0.1 goes there. Let's see, this is 4, right? So 1 over 2, half of negative 0.1 is negative 0.05. Okay, so that's my answer. So what this means is that if x decreases by 0.1, we expect y to decrease about 0.05. That's what that means. Okay, and then 19 and 21, you don't have to do a sketch. Okay, don't worry about doing a sketch. Okay, but compute delta y and dy. Okay, so dy is according to formula. Delta y is the actual change in y values as I move from 3 to 3.5, let's say. Okay, so okay, x squared minus 4x at x equals 3, delta x is 0.5. Okay, so dy by formula is derivative times dx. Okay, so dy equals the derivative is 2x minus 4 dx. Okay, now I just plug in. X is 3. Delta x, which is the same as dx in these problems. Okay, so delta x and dx are the same thing, little change in x. So 0.5 goes there from here, and I plug in 3. So 2 times 3 minus 4 is 2. 2 times 0.5 is 1. So that's dy. Delta y, it's actually a little bit harder. Okay, you plug in 3. So 3 here and 3 here, that's 9 minus 12, it's negative 3. 3.5 is definitely harder. It's 3.5 squared minus 4 times 3.5. Okay, just punch it in your calculator, right? Just get your calculator out and punch it out. I already did it. It's negative 1.75. Okay, so delta y, the actual change in the function value, is y2 minus y1. So negative 1.75 minus a negative 3, that comes out to be 1.25. Okay, but you can see it's a lot more work doing delta y than dy. Okay, dy was pretty fast. Didn't need to do any calculator. Very quick. Okay, change in change in y values is about 1. Okay, and you can see they're pretty close. So if you just want something quick and dirty, an approximate change in y value without actually having to figure out, what is 3.5 squared minus 4 times 3.5, and also what is 3 squared minus 4 times 3. Okay, it's a lot faster to do dy. All right. Okay, then something from 23, 25, 27. Okay, I'll do one of these. Use a linear approximation or differentials to estimate the given number. Okay, we will use a linear approximation. Okay, 1.999 to the 4th power. Okay, it's kind of messy, but we can approximate it, and the approximation is usually pretty good. Okay, so how do I do that? So I'll do 23, and you try to figure out 25 and 27 in a similar fashion. Okay, so 1.999 to the 4th power. So the function f of x is x to the 4th power. Okay, there's a nice close by value, right? What's the nice close by value? 2. So I'm using a equals 2. So 2 comma 16 is the order pair that I want here. All right, so I will find the equation of the tangent line, the L of x, so-called, down here, L of x. Right, so the function is raising something to the 4th power, x to the 4th. The nice number nearby is 2, 2 comma 16, 2 to the 4th is 16. Okay, so the derivative is 4x cubed. All right, plug in 2. So what's f prime of 2? Well, 4 times 2 cubed comes out to be 32. That's my slope. 2 cubed is 8. 4 times 8 is 32. So y minus y1 equals m times x minus x1. Okay. But now we have to keep going. So add 16 to both sides, clean it up. Y equals L of x, 32x minus 48. 32x minus 64 plus 16 is 48. Okay, so my linear approximation for this function, raising something to the fourth power, right? You know, most of us aren't very good at raising something to the fourth power, especially if you got weird decimals like that. But this is very nice. It's a straight line. So my approximation to 1.999 to the fourth power, which I can't get a hold of, is to plug in 1.999 to this linear function. So in other words, 1.999 to the fourth power, we're saying, okay, don't use x to the fourth. It's harder to do. Just plug into the linear approximation. Straight line. Okay, so I would only plug in 32 times 1.999 minus 48. That comes out to be 15.968. So my guess to the answer to 1.999 to the fourth power is 15.968. Okay, and let's actually see how good that is. So now on a calculator, 1.999 raised to the fourth power. 15.9680239. Our guess was 15.968. So we were correct to 5 digits, 15.968. In fact, the next one's even a 0. So it's accurate to within the 10,000th place, my approximation. So by doing a linear approximation, I got 15.968, which is wrong, but you can see it's not wrong by much. Okay. So that's the idea. Now, why do I want to do that? Because I like straight lines. Straight lines are easy to handle as compared to any other kind of function, right? Raising something to the fourth power, trig, logs, exponentials, square roots, cube roots, and so on. Okay, so you follow that format for 25 and 27. I will say a little bit more about it. So you have to come up with a nice nearby number, so to speak. For 25, it's the cube root of 1001. What's the nice nearby number? 1,000. And you know the cube root of 1,000. Cube root of 1,000 is 10, so it should be 10 point something. So the nice nearby number is 1,000. For 27, e to the 0.1, the nice number is e to the 0. So the nice nearby number is 0. Okay, so try that on your own for 25 and 27. 23, the nearby number I picked was 2, right? All right, so what are they asking for 29 or 31? Okay, again, they're showing you the back of the book, so to speak, kind of like problem 7 and number 9. Okay, show that secant of 0.08 is equal to 1 is a nice approximation. Okay, it's almost like saying, do 29 like 23, 25, and 27, and oh, by the way, the back of the book is 1. The back of the book is 0.1002. Okay, so that's all. Okay, so let me show you 29. Secant of 0.08 is approximately 1. Okay, so the nice nearby number is 0. So f of x is secant x at x equals 0. The nice nearby point is 0. Okay, what is the secant of 0? Well, secant is the reciprocal of the cosine. Cosine of 0 is 1. Reciprocal of 1 is still 1. So 0, comma 1. Okay, take the derivative. F prime of x, derivative of secant x tangent x. Plug in 0. F prime of 0 is secant 0, tangent 0. Tangent of 0 is 0. So my slope is going to be 0. Point, slope. Y minus y1 equals m times x minus x1. Well, this is all 0. Add 1. y equals 1. So yes, indeed, a good approximation for the secant of 0.08 is indeed 1. So it's something like, this is the back of the book. Okay, let me try to show you 31, similar theme. The 1 over 9.98 is approximately 0.1002. You're doing the same thing as 23, 25, and 27, and they're giving you the back of the book, so to speak. Okay. 1 over 9.98. So what's a nice nearby number? 10. Okay. So f of x is equal to 1 over x. Function is 1 over x, and we're near a equals 10. So we're going to use a linear approximation, okay, which is the tangent line essentially, but write it as a function. Okay, so f of x is x to the negative 1. What is the derivative of x to the negative 1? Negative x to the negative 2, which comes out to be negative 1 over x squared. All right, now I plug in 10. Plug in 10, negative 1 over 100, which is negative 0.1. That's my m. All right, so y minus y1, y minus 0.1 is equal to m times x minus 10. Okay, multiply that out and add 0.1 to both sides. Solve for y, in other words. So y equals L of x. What does L stand for? Linearization. The linear approximation to the function is negative 0.1x. Okay, this comes out to be plus 0.1. And then if I add another plus 0.1, it's plus 0.2. So that's my linear approximation. All right, now, instead of doing 1 over that, which is, a lot harder to do, it's a lot easier to just plug in to here. So L of 9.98 means just plug in 9.98 right here. So negative 0.1 times 9.98 plus 0.2 comes out to be 0.1002. Okay, so by using the linear approximation, I'm going to guess that 1 divided by 9.98 is approximately 0.1002. And you can see that's exactly what we have over here. Okay, and yes, the problem's finished, but just for fun, let's actually try 1 divided by 9.98. 0.100204. We said 0.1002. So we got 100200 all correct. 1, 2, 3, 4, 5, 6 digits correct. It isn't until the 7th digit after the decimal point that they're different. Okay, so pretty good approximation, as you can see. Okay, then the last one was 33, and then I'm pretty much done. The edge of a cube was found to be 30 centimeters with possible error in measurement of 0.1 centimeters cubed. Okay, so that means it could really be, what, 29.9 to 30.1, somewhere in that range, plus or minus 0.1. Use differentials to estimate the maximum possible error, relative error, and percentage error in computing the volume and the surface area of the cube. Okay. Do that. Okay, so I drew myself a cube. Side length x. X is 30 centimeters plus or minus 0.1 centimeters. Okay, so let me start with the volume. The formula for the volume of a cube given a side x is x cubed. So dV equals 3x squared dx. Now, it also asks for the surface area. So how do I find the surface area of this cube? Well, each face is a square. if a side length is x, the area is x squared. There are 6 of them, so the surface area is 6x squared, right? There's the front, the back, left and the right, top and the bottom. So 6x squared. Right, so dA, little change in area, is derivative of this is 12x dx. Okay. All right, so dV is, use this formula, 3 times x squared dx. So x is 30. dx is 0.1. That's the maximum possible error, right? So I plug in 0.1. So 3 times 30 squared, plug in here, times 0.1, punch it in your machine, comes out to be 270 centimeters cubed. So that's the maximum possible air in the volume that I might have if I declare that the volume, if I declare a side to be 30, but you might be off by as much as 0.1, either plus or minus. So what's my maximum air and volume, right? It'd be 270 centimeters cubed. Okay, do the same thing for the area. My possible change in area is 12x dx. So 12 times 30 times 0.1, punch it in the machine, 36 centimeters squared. That's the maximum air in the area. Okay, now they say the possible percentage change. Okay, so the volume would be 30 cubed, right? If each side is 30. So the volume is 30 times 30 times 30. 27,000. So the possible percent change in volume. So if I'm off by 0.1 centimeters, right? What's the possible percentage air that I could be? Well, 270 divided by 27,000, which is 1%. Okay, so the maximum possible air I could have in the volume is 1% if I declare plus or minus 0.1, right? So not too bad if you're willing to live with 1% air. And then do the same thing for the surface area, right? The actual surface area is 6 times s squared, 6 times x squared. So 6 times 30 squared, 5,400 centimeters squared. So what is the possible percentage change in area? Well, the maximum possible area is 36. Divide that by the actual area, which is 5,400. Okay, that comes out to be 2 over 300 or 1 over 150. That's 2/3%. So the maximum possible air in surface area is 2/3%. Okay, and that's it, folks. So I'm now done with 3.10. So just want to see where I'm at. Okay, so I'm up to here. So I have tomorrow and Wednesday to do 3.11, which is on hyperbolic functions. Okay, I'll give you a small introduction today. So I'll be done in a few minutes, and then I'll turn it over to questions if you have any. So you can start putting in the chat, or you can unmute yourselves at that point. But if nobody has any questions, I'll just be finished, and that'll be it. Okay, so I'll be done in a few minutes. 3.11 is on something called hyperbolic functions. So I'll just show you what you need and the relevant pages. Okay, hyperbolic functions. Page 259. Okay, now it looks like sine, cosine, tangent, cosecant, secant, and cotangent, but you put an H after it. That's exactly what it is. Notice it's the same 6 trig functions, sine, cosine, tangent, cosecant, secant, cotangent, but there's an H, which stands for hyperbolic. So very technically, this is hyperbolic sine, hyperbolic cosine, hyperbolic tangent, hyperbolic cosecant, hyperbolic secant, hyperbolic cotangent. Okay, that takes too long to say. Okay, so I'll give you my own hangups. Okay, so this is not standard. This is just the way I like to say it. Now, some other teachers say the same thing, but I usually just say cinch for this. Cinch, like the English word cinch, C-I-N-C-H, cinch. This one I say kosh, or sometimes I hear kosh or kosh. I don't really know how to say this. Tan, something like that, or just add an H afterward. Okay, these, I don't really know how to say any of these, except we don't use them that much. So I'll just say hyperbolic, or maybe that kind of looks like cough. Okay, but anyway. Okay, the two that you want to focus on mostly are these. You can put these on your cheat sheet. Okay, sinh, hyperbolic sine, e to the x minus e to the negative x all over 2. Cosh, hyperbolic cosine, e to the x plus e to the negative x over 2. So these are very similar. Okay? And again, if we were meeting face to face, I'd make you guys memorize these. Okay, so, there we go. They both have e to the x. They both have e to the negative x. They're both divided by 2. This one's a minus, this one's a plus. All these others follow the roots just like trig. So notice hyperbolic tangent is sinh divided by cosh. That's just like trig. Should be just that divided by that. And guess what these are? These are exactly the same reciprocals as they are for trig. So hyperbolic cosecant, reciprocal of sinh. Hyperbolic secant, reciprocal of cosh, just like trig. And hyperbolic cotangent, reciprocal of hyperbolic tangent. Okay, so that's what's happening here. Okay, now, there's a lot more stuff in this section, so I ought to tell you right now what you need to know and what you don't need to know. Okay, you don't need to worry about any of these. Page 260, identities. Okay, we had trig identities, right? There are hyperbolic identities. Okay, here they are. You can look at them or not, but don't memorize any of them. I would say don't put any of them on your cheat sheet. Okay, if we met face to face, I wouldn't have you memorize any of these. But there's some things that are a little bit different. As you notice, we had sine squared plus cosine squared equals 1. It turns out cosh squared minus sinh squared is equal to 1. Okay, you have these other weird identities also. Okay, that looks like something from trig, right? The sine of x plus y is sine x cosine y plus cosine x sine y. Something similar happens for sinh and cosh. But anyway, so don't memorize any of these or don't use any of these. Okay. How about the derivatives? On page 261, I want you to know these three. Okay. There are derivatives of hyperbolic secant, cosecant, and cotangent. You're not responsible for these. You are responsible for these, but you can see that they're not that bad. Derivative sinh turns out to be cosh. Derivative cosh turns out to be sinh. That's nice. They are derivatives of each other. And how is it when trig? For trig, the derivative cosine was negative sine, right? But for the hyperbolics, they turn out to be derivatives of each other. And look at this. This is nice. Derivative of hyperbolic tangent is hyperbolic secant squared. That's just like it was in trig. Right? So you're responsible for these three. You are not responsible for these three. Okay. And you're not responsible for anything else. Okay. There are inverse hyperbolics. You don't have to worry about those too much, or definitely don't memorize them. We actually have a couple of problems involving the inverse hyperbolics, but don't memorize any rules like this. 262. There are actual ways to get rid of sinh inverse, cosh inverse, and hyperbolic tangent inverse. They're nice, but don't even look at them. Don't memorize them, don't look at them. The inverse hyperbolics have their derivatives. Don't worry about these. I won't have you responsible for any of these at all either. Okay. And then the problems begin. Okay. So I'll show you the problem so you can get started with it. So here's that. And a little bit more. And then on the next page. And that's about it. Okay. So that's an introduction to the hyperbolics. I'll get started with that maybe tomorrow. Okay. But now let me turn it over to you for questions and answers. Okay. So let me stop the share and check the chat. Okay. Let's see. 3.10, 15, 3.4, 35, 41, 47, 3.9, 23, Can you use negative b over 2a to find the highest point in a projectile? Not for now anymore. Now that we know we're supposed to take a derivative and set it equal to 0, that's what I want you to use from here on out. Okay, 3.249. Okay, so I definitely can't get to all of these. 3.8, number 5. Okay, and thank you, Prasanna, for what you have there. Okay, I'll do some of these. I probably won't get that far, but we'll see how it goes. Okay, and might have to priority some of these. If I don't get to all these, you can ask again the next day or the next day or the next day all the way to Thursday. Okay, so get my clipboard here. So I guess I'll go in order of where I was. Okay, so go back to sharing the screen. Okay, 3.249. And let's make this every day this week. I'll try to leave you some time for question and answers every day since I'm almost done. So same thing tomorrow, same thing Wednesday. If I leave you some time, go ahead and ask questions. And I'll try to devote all of Thursday for Q&A session, questions and answers, okay? 3.2, number 49 was asked for. Let me see. Okay, so that one requires us to look at the picture. Okay, so u of x equals f of x, g of x. Okay, so let me hide the text for a moment. So u prime of x by the product group is f of x, g prime of x plus g of x, f prime of x. That's the product group. Okay, and then I'm supposed to plug in 1. So u prime of 1 is f of 1, g prime of 1 plus g of 1, f prime of 1. Okay, the primes mean slope. The f's are just the graphs. Okay, so f and g of 1. Okay, f of 1 is 2. G of 1 is 1. Okay, the primes mean slope. So g prime of 1, what's the slope here? Looks like it's negative 1 over 1 and down 1. F prime of 1, what is the slope at 1? Okay, that's over 1 up 2, so it looks like it's 2. So that's going to be what? Negative 2 plus 2 equals 0. Okay, and to save time, I'll just say something similar for B. Okay, use the quotient rule, plug in 5. Okay, so as far as I'm concerned, I'm done with 3.249. If somebody still has a question with it later, you can go ahead and ask, but in the interest of getting more questions in, 3.4 had some questions here. 3.435. 3.435, okay. Y equals the cosine of parentheses, 1 minus e to the 2x over 1 plus e to the 2x. Okay. Okay, so the outside function is the cosine. So the derivative of cosine is negative sine. So negative sine, the whole thing. Okay, so that's done. And then by the chain rule, it's times the derivative of the inside function, which involves a quotient. So now it's a great big quotient rule. Okay, so bottom times the derivative of the top. Derivative of negative e to the 2x is negative e to the 2x times 2. Minus the numerator times the derivative of the denominator, e to the 2x times 2 all over 1 plus e to the 2x quantity squared. And I'll just say etc. That's essentially it. You can clean up the algebra, but you can do that as well as I can, or maybe better. So I'll abandon that problem. Okay, let's see. What else do I want to do? 47 of 3.4 also. Try that one. Y equals cosine of the sine of 3 theta. So again, the outside function is cosine. So y prime is negative sine 3 theta times the derivative of sine 3 theta, which is cosine 3 theta, times the derivative of cosine 3 theta, which is 3. So how about I rewrite it as negative 3? Why don't I put this in front? Negative 3 cosine 3 theta sine of sine 3 theta. So that's first function. That's second function for y double prime. Okay, so for y double prime, first times the derivative of the second, derivative of sine 3 theta is cosine sine 3 theta times the derivative of sine 3 theta, which is cosine 3 theta, times the derivative of cosine 3 theta, which is 3. So all of that was first times the derivative of second. Derivative of sine 3 theta is the cosine of sine 3 theta times derivative of the inside, which is cosine 3 theta times 3, plus second function times derivative first. So derivative of negative 3 cosine 3 theta is positive 3 sine 3 theta times the derivative of 3 theta, which is 3. Okay, so again, that's essentially a little bit of touch up, like 3 times 3 times 3 is, whoops, sorry, 3 times 3 is 9. And you can take 3 times that, 3 is 9, and so on. Okay, that's as much as I think I want to do right now. Let's see, only 5 minutes left. 3.8. 3.8, number 5. Okay, so there were several parts to it. Maybe I'll just get started with A. Okay, so let me get down the key data for that one. 3.8, number 5. So for part A, they want 1750 and 1800. So the year 1750, the population was 790 million. And then 1800, 980 million. And use that to predict the world population in 1900 and 1950. Okay, key thing that I want you to notice is that from 1750 to 1900, that's 150 years. Okay, so for the year 1900, T is 150. And for the year 1950, T is equal to 200. So at the appropriate time, I'm going to be plugging in 150 and 200. That's a key thing for that. Okay. So A of T equals A0 e to the KT. So we're starting at the year 1750 with 790. So 790 goes here. Okay, and then 1800 means 50 years. So I plug in 50 here and 980 here. So 980 equals 790 e to the 50k. Divide by 790, divide by 790. So 98 over 79 equals e to the 50k. ln, natural log of 98 over 79 equals 50k. Divide both sides by 50. Punch it in the machine. So natural log parentheses 98 divided by 79. And then take that answer and divide it by 50. 0.00431. Okay, that goes way back over here. So AFT is 790 e to the 0.00431t. Okay, that pretty much clinches it. So now if they give me any year that I want, like 1900 and 1950, so we agreed that for the year 1900, time was 150. So just plug in t equals 150. And this is population, so population is rounded to the nearest whole number. And likewise for the year 1950, plug in t equals 200. Okay, maybe I have just enough time to do this one. So let me just try to do that one, all right? So plug in 150 right over to here. Okay, so I've got 790 e to the parentheses answer times 150. Okay, so that goes there. We got 1508 roughly million, or 1.5 billion more accurately. So the world population in the year 1900 was 1.5 billion. Okay. All right, folks, looks like we're out of time, so that's all the time I can do for today. So sorry about that. Okay, so we can continue tomorrow. We'll see how it goes and go from there. All right, so I think that's pretty much about it, folks. So have a good day. So tomorrow I'll get started with the hyperbolics. I'll try to leave you some time at the end for questions and answers tomorrow and Wednesday in preparation for the test. All right, that'll do it for today, folks. So have a good afternoon. We'll see you all next time. Okay, bye everyone. Thank you.